Welcome to the February 2018 Bay Area Rust Meetup. Tonight, Matthew Forniciari is going to talk about chaos experiments with Gremlin, and George Morgan is going to be talking about embedded programming with Flipper.
Awesome. Thank you so much for coming today. Today's a really special day for me. I've been working on Flipper for just about 4 years now. And right before this talk, I actually open sourced everything. So Flipper is an entirely open source project as of just a few hours ago. And so, thank you. And so I'm really excited to be launching this project that I've been working super hard on. So a little bit about me. My name is George Morgan. I really enjoy anything low level. So anything like hacking old video game consoles, working with retro hardware. That's right up my alley. I also really enjoy studying operating systems, really right at the bare metal. That's my stuff. I'm currently studying computer engineering at RIT in New York, but I've recently decided to move to the Bay Area and take some time off of school to pursue launching the startup Flipper. I've been working with embedded systems for just about 5 years now. So embedded systems. I just want to do a quick poll of the room. How many of you guys have used an Arduino or Raspberry Pi or embedded systems? Awesome. Okay, cool. So a bunch of you guys are familiar with them. But for those who aren't familiar with them, they're basically just small general purpose computers. And they serve one purpose, which is basically to connect software running somewhere to physical things in the real world, hardware. And these things that you connect to embedded systems could be sensors, motors, displays, really anything you can imagine. And you plug them into these standardized ports that are on the embedded hardware, these buses. So embedded programming, embedded systems have been programmed the same way that they always have been for a long time. Basically, you have a computer, you write some code on that computer, it's built, and then it's flashed to an embedded system, and every time you need to make a change to this code base, you have to reflash this code to the embedded system again, and this is a time-consuming process. Also, to debug software that's running on an embedded system, you need an external debugger. You have to connect it with wires. The tools that are provided for embedded development generally aren't as polished as app development tools because there really aren't as many embedded developers as there are application developers. And as a result of all these factors, there's a pretty steep learning curve that's required to get started with embedded. So out of all the things that an embedded system is used for, the most common thing we see is connecting some sort of application, a web app, a mobile app, a desktop app, to some sort of embedded hardware to get sensor data or display something on a display. And ironically, even though that's the primary use case, connecting apps to embedded system is actually really, really difficult. To connect to an app to an embedded system, you have to structure an API, create a communications protocol, write drivers, serialize and deserialize information, create bindings for a language, support an SDK. And then you got to repeat this over and over again for each language that you want to support and each platform that you want to support. And this is pretty discouraging. I know a lot of people who are really interested in doing awesome embedded projects, but they're deterred from the fact that it's super difficult to get an app to communicate with an embedded device. So, when I ask my friends what they think of embedded systems, they think they're pretty scary. They're often viewed as obstacles to completing projects. When an embedded system is needed, they're often avoided entirely or they're completely glazed over. And the truth is embedded systems are actually pretty complex. So I think it's about time that we rethink embedded programming. There must be a better way to do this kind of thing. And that brings me to the history of Flipper. So Flipper started in 2012 as a research project that I was doing to figure out how to make embedded systems more accessible. And the goal of this research project was to create an object-oriented operating system and then specifically design some embedded hardware to run that operating system. And over the course of 2012 to 2014, I published 3 different research papers through the Society for Science detailing kind of how I went from nothing to making a really robust and accessible embedded system. And actually in 2014, Flipper's programming model was recognized by the IEEE. So what is Flipper? Well, it's an entirely new kind of embedded development tool. It completely rethinks the traditional embedded programming model. And in a nutshell, what Flipper does is it makes it super easy to connect applications written for mobile, desktop, or web platforms to communicate with embedded hardware. Another way of describing this is that it's hardware that acts like a software library. So the main selling point of Flipper is that you can use the tools that you already know how to use to develop code that ends up controlling an embedded platform. So if you're an iOS developer, you're going to be familiar with using Xcode and Swift and Objective-C. You're going to be really knowledgeable about those tools. If you're an Android developer, you're going to know how to use the Android Studio and Java. You'll know how to use those tools. But you might not know how to use embedded tools. What if we can let people work with embedded systems using Java in the Android Studio or using Objective-C and Swift in Xcode? This is exactly what Flipper is trying to accomplish. So along with the using tools you already know how to use, that means that you can also use any language that you know how to use. So we're making an effort to support as many languages as we possibly can across as many platforms as we possibly can for people to get started using the device. So we've got a variety of languages under development actively, mainly C and C++. We've got bindings for Objective-C and Swift, even in interpreted programming languages like Python, web languages like JavaScript, and even functional languages like Haskell. And of course, we support Rust, which is why I'm here today talking to you about the Flipper platform. So before I move into more of the hardware architecture of the platform, I want to talk to you a little bit about the hardware. And I think a really good way to do that is show you the evolution of the hardware device. So this is the first iteration of the Flipper device. As you can see, it's really nothing more than just a jumble of wires on a breadboard. But as I learned how to design and develop printed circuit boards, I was able to shrink that down, yielding kind of the first iteration of the Flipper platform, or the second. And once I kind of worked out some bugs in that, we get to the third revision of the Flipper hardware. And it's printed in this beautiful matte black solder mask, and I really dressed it up to look nice because I thought it was going to be the final hardware revision. But there's always one more thing to do, so that brings us to the fourth iteration of the Flipper hardware, and this is what we've got today. So the specs of the hardware, for those of you that are interested, it's got 120 megahertz ARM Cortex M4 CPU, a respectable 1 megabyte of internal flash memory, and 128 kilobytes of internal SRAM. It's also got 8 megabytes of external memory for logs, images, any sort of data that your application might need to use or write to. It's also got all of the standard embedded peripherals that you would expect to have these days: GPIO, analog pins, I2C, SPI, USART, and even USB. So Flipper is pioneering a new form factor for embedded systems. And this is mostly thanks to these right-angle connectors that you have on the bottom of the board. These are really awesome because it enables the Flipper board to be used on or off of a breadboard. You see, with traditional embedded systems, you kind of get to make a choice. You can either buy an embedded system that you plug into a breadboard and you use it there, or you buy an embedded system that you just plug wires into and you use it kind of off of a breadboard. But with Flipper, you really get the best of both worlds because it ships with these two right-angle connectors, and if you plug these into the Flipper board, you can insert it into a breadboard. Pretty simple. So here's our final hardware product, or a render of it at least. It's called Flipper Carbon, and we have 250 of these being made right now. It's going to be made in matte black solder mask and have high manufacturing tolerances. I really wanted to create a board that people would go, wow, that looks awesome. And I'm also proud to say that these are made right here in the US. So software, this is the gateway to the embedded system. There are 2.5 ways to run code on the Flipper device. The first way is the one that you'll be familiar with. You can run code standalone on the embedded hardware, compile it, put it on the hardware, it lives there running. But then the second way, which really defines the way that you use the Flipper platform, is you can run code on a host computer and control the device remotely. And then third, you can combine these two together in an interesting way that we'll explore in a second. So creating code that runs on the device is super easy. Pardon my C example here, but we're still working on getting the Rust tools set up to compile to the hardware. You just create a main function, put your API calls in here, and then our build system will build that. You can run make run, and then it'll be loaded directly onto the embedded system and start running. But what if I want to create an application that runs on the host? Well, actually, it's exactly the same as creating an application that runs on the device. Just create a main function, put your API calls in there, and run it. And this is all due to the fact that the C API is completely portable between the host and the device. What this means is that you can develop and debug your program logic in C on the host, and then compile that down to the device for free after your program is working properly. This third thing I mentioned, which is a combination of the two, is you can run device code from the host. And the way this works is through what we call modules. So modules are basically just dynamically loaded libraries that exist on the device. And here's a quick example of that here. We've got a function called myPackageFunction, and that lives on the device. And on the host, we have a main function that calls the function. And behind the scenes, when you run that function on the host, what's actually happening is our tools are performing a remote procedure call to the function on the device. So when you run this host program and myPackageFunction is run, the host pauses execution. A command is sent to the device to run the device function. The device function runs, returns, and then the host will print the value that it actually got back from executing that function on the device. So as I touched on, modules are basically just dynamically loaded libraries that live on the device, and they have functions inside of them that can be called from the host. What's also really cool is that these are loaded at runtime of the host program. What enables modules to work are bindings. And so bindings are basically just a set of functions in a host program that call these counterpart functions on the device. And right now, our tools automatically generate these bindings for C. So any function in C you create for the device, you can get a function with that same signature on the host that calls that function on the device using a remote procedure call. The device always has the right code on it. Remember how I mentioned that the code is loaded on the fly? Well, when we build a binding for a particular module, we actually embed the device executable code directly in that module. So anytime the host goes to perform a remote procedure call, if the device either doesn't have the code that it needs to execute on it, or the code is out of date, we actually just push it over and load it in real time. So the user never has to worry about installing packages to the device or managing device state. So Rust bindings. Rust can control the Flipper hardware right now. All you need to do is include the Flipper crate, plug in your board, and get started developing an application. And since this is a Rust app that's running on the host computer, you'll be able to debug it just as you always have normally been able to debug code. So here's a simple application that connects to a Flipper device, grabs its UART0 bus, and then writes hello world out of that bus. So that's one thing I really, really want to hit home, and it's that you can debug using the tools and the methods that you already know how to debug with. So for example, this is a simple application that I put together that just uses 3 sign functions to kind of compute different varying brightness levels of the LED to produce an interesting color pattern. And what's really neat about this is that I can hit a breakpoint up here, and each time I press continue in the debugger, I'm looking at my board and I'm seeing the LED change color. And because I can look at what my board is doing and then see the code, that feedback loop there enables me to determine what's going wrong. With traditional embedded systems, if you wanted to be able to debug code like this, you would need to buy an expensive embedded debugger, which can be upwards of $100, attach it with a bunch of wires to your hardware, learn how to load the embedded tools on your computer, attach an embedded debugger over a port, install drivers. It's really just a messy process. But with Flipper, you're debugging right on the host computer using the native debugging tools on the host. So to kind of paint a picture in your mind of what the Flipper platform can be used for, I want to tell you a little bit about some of the projects that I've done with it. So I mentioned that I was really into old video game hardware. And one of my favorite consoles is the NES, straight out of the 80s. So the NES has inside of it a chip called the PPU. And the PPU is basically, it stands for Picture Processing Unit, and it's basically just the graphics processor of an NES. And so I desoldered that chip from a real NES, and I recreated all of the circuitry around it on a breadboard that's needed for that chip to function. But instead of connecting the PPU up to the CPU, which would tell it commands like what to draw, I connected it directly up to a Flipper board. And you can kind of see up here in the top of the picture is my MacBook Pro. I downloaded an open source emulator, and I modified that emulator so anytime a write was made to the video memory inside of the emulator, instead of sending it to the virtual PPU so that you could see what's being displayed on the screen, I send that to a module on the Flipper board, and it twiddles the physical bits necessary to write that information into this chip. And the result of that is that we can see what the emulator is displaying on a real screen connected up to this whole system. This took me about 20 lines of Flipper code, and I only spent maybe about 15 minutes writing the Flipper code necessary to get this to work. I got to spend most of the time on this project learning about what I wanted to learn about, which is the hardware architecture of the NES. Moving on, this is another really cool example we did. Here's my friend Nick, and he's connected a Leap motion controller up to his Linux laptop. And he wrote just about 10 lines of Python code that reads the position of the hand over the Leap motion controller. And as he's moving his hand up and down, we're mapping that position of his hand in 3D space to the brightness of the LED. So you can imagine extrapolating this to any other kind of device, like put on an Oculus Rift headset and bring sensor information from the real world into your virtual environment. So to demonstrate the more IoT capabilities of the Flipper platform, I connected a prototype of our Wi-Fi shield, which lets the Flipper board talk over a network, as well as some sensors like a temperature sensor, a humidity sensor, a water sensor. And I put that all in a box, and then I wrote an iPhone application that just sucks the sensor information in from the Flipper board and displays it in some graphs over time. Once again, about 10 lines of Flipper code to make this work. I spent the majority of the time on this project doing what it is that I wanted to do, which is building the app, instead of fighting with an embedded system or focusing on the pathway to get the data from the app to the embedded system. And I think that this is probably my favorite project that we did with the Flipper platform. Once again, my friend Nick built this super awesome robotics platform called Kudos. And in one afternoon, we decided that we wanted to drive it around with an iPhone. So we connected a Flipper board to the robot, and in about 10 lines of Flipper code, I made some sliders on the iPhone app, control the speed of each motor. This was awesome because we drove it around our school RIT, and it turned a lot of heads. It was a great project. So these examples demonstrate the versatility of the Flipper platform. As you can see, like these projects were done across a variety of platforms. We used a Linux computer, we used a Mac, we used an iPhone, and we used a variety of different languages too. We also used lots of different kinds of hardware. There was a robot, a Leap motion, some sensors, and we even used something as crazy as a PPU from an NES. So in order to use the Flipper platform, the tools will be your best friend. And if you're getting started with the platform, the tool that you'll probably first come in contact with is the console. We are super huge fans of Rust's approach to getting people to start working with a new programming language. The way that Cargo works is absolutely awesome. And we decided to borrow some ideas from Rust and incorporate those into the tools that will help our users get started with an embedded platform. So the Flipper console is entirely written in Rust, as are most of the tools that power this device. And currently the console is responsible for creating projects for the Flipper, generating the module bindings for the C language that I was talking about, as well as uploading new firmware and stuff like that. So the console is built to be super extendable. So in the future, we hope to be able to generate more than just language bindings for C. Here's the handlebars template that generates the C language binding. You could easily take this and extrapolate it and have the tools generate bindings for any other high-level language. So after this talk, if you rush over and you clone our Git repository, the first tool that you'll probably be interested in using is FVM. FVM is essentially the iPhone simulator of Flipper. So it enables you to develop and debug Flipper applications without actually having a physical Flipper device attached to your computer. So here is a simple example where we're connecting to an FVM over localhost, setting an LED color, writing a GPIO pin, and we can see the side effects that the board would be performing if it were attached to the computer. If you're more interested in like firmware development, like low-level operating system development, you really want to kind of roll your own low-level firmware for the device. We've got this tool called FDFU, and basically what it does is it flashes new firmware images to the device without the need for external hardware. So you don't need to plug in any extra device to flash firmware. Just pass your firmware image to this tool and it'll put it right on your Flipper board. And probably the most simple, but I think the most significant tool for use with the Flipper board is fdebug. So with traditional embedded systems, if you want any sort of information about what the board is doing on your host computer, you've got to get out a USB serial converter, connect it to your board, set up a USB serial program, make sure your baud rates are right, install drivers. It's a super headache. Whereas with Flipper, fdebug pipes the STD out of the device to the STD out of your host. So just plug your Flipper board in, run fdebug, and then whatever your device is printing, you'll be able to see right there in the terminal. So, like I said, we started manufacturing these very recently, and you can get a board today for only $50. We expect to be able to deliver these in March. So if you're interested in grabbing a board, super thank you for doing that, and you can head over to flipper.io. I'd also like to give a special thanks to some people who've really stuck with me on this project. That's my best friend Nick Mosier, my friend Travis, Harlan, and Dan. You guys have been super awesome in helping me contributing to this project. Big thank you to you all. And last but not least, contributing. We want to make Flipper into a full-fledged embedded development platform. And the way that we think would be best to do that is by collaborating with the Rust community. We think that the Rust language is absolutely fantastic, and we would absolutely love to bring Flipper and Rust together. To do that, we've decided to open source as Apache v2, just like Rust, and we really welcome your contribution. So if you're interested in contributing, check out the organization github.com/flipper-io. And once again, if you're interested in picking up a development unit, go to our website, which is flipper.io. So I can answer some questions now. Thanks so much for coming again, and that's about it.
Hi. I'm just wondering, what's the power usage like of the board, and does it vary according to how much you're doing with it?
So the board basically consumes no power at all. It's basically around 20 milliamps when the board isn't really doing anything. If you've got like an LED or anything that draws power attached to the I/O pins that aren't powered by an external supply, then the amount of current that the board is going to be drawing will go up. But it's fairly low when the board is idling or running very simple programs.
I just wanted to ask a clarifying question. So you had this whole list of languages that you said you could use, but those are only for running on the host, right? The modules have to be written in C.
Right. So all the languages we support that currently aren't C or C++ need to be run on the host. And they can be run on any platform that supports running those languages. You can build modules or code for the device in C or C++, and we're working on figuring out a way to get embedded Rust to run on the device as well, directly.
One more question. What's the throughput of the RPC interface?
Right, that's a good question. So the RPC interface is limited by the USB 2.0 bus speed. And the way that the USB interface works is you've got these things called interrupt requests, and the computer services them once every millisecond. So that means that you can perform one RPC every millisecond. But there's also some interesting things you can do to chain a whole bunch of events together. So you can push a whole bunch of RPCs out at once, or also push a bunch of data to the board at once too.
Thanks.
What would it take to be running Flipper on non-Flipper hardware?
That's a good question too. Currently, we only support the Flipper hardware. If you wanted to run what is called the Flipper message runtime, which is really the core RPC protocol of the Flipper device on, say, an Arduino or Raspberry Pi, you would just need to create what's called a board support package to be able to connect to the physical hardware peripherals of that device. You would also lose some of the functionality of the Flipper board if you did it that way, because on our hardware we have two chips. One of the chips handles controlling all USB communications to the host, and that's responsible for doing things like flashing the device, in certain operations, stopping the ARM processor, power cycling the ARM processor, doing things that really make the ease of use of the board very high. But theoretically, you could run the message runtime on another embedded system.
So you said that the RPC throughput is limited by the USB bus.
Right.
And when you're writing, like when you generate these RPC stubs, presumably there are some contexts where you do that wanting to connect over Bluetooth or Wi-Fi or
Right.
some generic transport. Does the same RPC protocol, like, can you use it in other contexts than USB? Or is the USB context the only way you can use that right now?
Absolutely. So you totally can use it over any of what we call endpoints. So an endpoint is a Bluetooth device, a USB device, even another Flipper device. You can do RPCs over any of Flipper's buses, so I2C, SPI, USART. But right now, we don't sell the adapter that gives the device Wi-Fi capabilities or Bluetooth capabilities. So if you picked up a board today, you'd be limited by USB. But in some of the IoT prototypes we did, we were definitely using a Wi-Fi device. And the performance is basically just about the same, depending on the network conditions.
Can you talk briefly about what like the current obstacles are for writing the on-device code in Rust?
So there's a huge amount of work being done in the Rust community right now, mainly by Reparic, I think it's called. His name is, and to basically create a very minified version of the standard library that can be run on embedded systems. There are a variety of embedded systems that do already support running Rust code, and we've done some super limited test exercises where we have run Rust code on the hardware, or at least hardware that's very similar to Flipper's hardware, on an ARM processor at least. So it should be totally possible to do. No guarantees that you'll be able to call Rust functions just yet, but that's absolutely something that we could integrate into the future.
Yeah, I think it's awesome that you can use the Flipper virtual machine to like go home right now and start getting to work with the Flipper. But what's the cost looking like when this ultimately comes out?
So it came out today, and you can buy one for $50.
Awesome, thanks.
Yep. Thanks, guys.
Thank you all for coming. Thank you to Matthew, to George and Forney for speaking. As always, you can stick around for a while. If you have any ideas for talks for future meetups, please let me or Boats know. Boats is somewhere. You saw Boats. Yeah, thank you.